Okay, so for Unit 8, the topic is on carbonyl compound. So this is another type of functional group that you all will learn. Okay, it involves the carbon that has a double bond with oxygen. So before we go through on the chapter, so at the end of this unit, the outline or what you should be able to uh, get by the end of the topic is first is to identify what is the carbonyl compound, name, draw, and the molecular structure of carbonyl compound. So there are two types of carbonyl compound that you have to know. One is aldehyde and the other one is ketone. So the difference is the position in which the carbon double bond O is situated, whether it is at the end, which we call as the terminal, and then or whether it is in the middle. Okay. Number two is you should be able to know the preparation for both aldehyde and ketone. Here I have include several types of synthesis in which that we can obtain carbonyl compound. And then we will see some of the differences in terms of properties for aldehyde and ketone. Okay, even though some of them may have the same chemical formula, but because of the different position of the carbon double bond oxygen, C double bond O, the whole properties will be different. And the last part will be, we will see some example for the reaction of aldehydes and ketone. So on to the introduction. So basically, uh, a carbonyl compound, okay, an organic compound that are having a carbonyl functional group. So what is the carbonyl group? So if you see in an organic compound, if it's contains C double bond O, so that means you can consider that as a carbonyl group uh, organic compound, okay, or a carbonyl uh, contain organic compound. So some example are as aldehydes and ketone and also carboxylic acid. But in carboxylic acid, it contain a carbonyl group C double bond O and also OH, a hydroxy. So it is like a combination of alcohol and also a carbonyl group, functional group. But for carboxylic acid, there is a whole individual topic, which is in topic 9. So for this particular unit 8, we will be focusing on aldehydes and ketones only. So this is the C double bond O that I have mentioned, which is the carbonyl group. Okay, it must contain C double bond O, and then you have these two bond line, meaning that it can be R group, okay, alkyl, or it can be AR, which is aryl group, or it can be just hydrogen over here. Okay, so in aldehydes, so for aldehyde, the carbonyl group is at the end of the carbon chain and so has at least one hydrogen attached to it. So you have this C double bond O, okay, but one side of the bond must be hydrogen because the C double bond O will be at the end, or what we say as the uh, terminal carbon. Okay, the term that we use is terminal carbon to tells you that the position of the carbon is at the end of the chain. Okay, while the other one must be an R group. It can be alkyl, it can be an aryl group, aromatic or aliphatic, doesn't matter, as long as there is another carbon attached here. So it can be CH3, for example, the simplest one, or it can be any other number of carbon as well. So that is aldehydes. While for ketone, okay, for ketone, both sides of the C double bond O, okay, the carbon that is bonded to the C double bond O must be an R group. Okay, meaning that the carbon does not uh, bonded with any hydrogen. Okay, it must be bonded with carbon, which is alkyl group or aryl group. Okay, so you have R over here, and the other one is written as R prime. R prime meaning that both of these can be different. So let's say you have CH3 over here. This side may be CH2, CH3, for example. Okay, it doesn't have to be necessarily the same. Okay, it doesn't have to be necessarily the same. Let's say you have CH3, this one also must be CH3. No. So it can be CH3 over here. Let's say over here you have C4 carbon, there is 4 carbon on this side. So it is still a ketone. So if you look over here, the position, aldehyde, C double bond OH. Okay. So if you want to uh, easily identify whether the compound is aldehyde or ketone, you see where is the position of the C double bond O. If it is at the end of the chain, then it is an aldehyde. But for ketone, the position of the C double bond O is in the middle. Okay, it is between two carbon. Okay, one carbon, two carbon. Okay, there must be two carbon on each side. So aldehydes and ketones cannot be distinguished by their molecular formula because they have the same functional group. Meaning that if you have, they may have the same chemical formula. If let's say for a 3 carbon, for example, here we have an aldehyde and ketone. So what is the molecular formula for the aldehyde and ketone below? So an aldehyde over here, we count, we have 1, 2, 3, 3 carbon. How many hydrogen? 1, 2, 3, 4, 5, and 6. So there is C3H6O, okay, because there is only one oxygen. While for this ketone, 1, 2, 3, also 3 carbon. How many hydrogen? 1, 2, 3, 4, 5, 6. So C3H6O as well. So both of these are having the same chemical formula. So if you just write it as a chemical formula, it is hard to distinguish whether or to differentiate whether it is an aldehyde or ketone. Okay, so in order to do that, it is better to draw in a way that you can tell where the position of this C double bond O. Okay, so this is an aldehyde because the position of this C double bond O is at the end. Okay, you have hydrogen attached to this carbon, while this is a ketone because this carbon over here is bonded to another carbon, and on this side also another carbon. So let's see on how the naming of these aldehydes and ketone. So aldehydes are named using the suffix al or al at the end of the name. For example, from normal alkane, ethane, you are going to change it, remove the e and add this suffix al. So from ethane, it will become ethanol. From propane, propanol, butane, butanol, and so on. Okay. Example, here you have, if there is only one carbon, C double bond O, H2, okay, so the name will be methanol instead of methane, so it will become methanol. From methane, become methanol. And then from ethane, 2 carbon, it will become ethanol. Okay, 3 carbon, propane, propanol, and then butane, butanol for 4 carbon. Okay, but you have to see that all of the C double bond O H is at the end. Okay, it is at the end. So for example, like this butanol, it can be on this side or it can be on this side. As long as it is at the end, so it will be an aldehyde. So if you look over here, there is also a name that is in bracket. So this is known as common name. The one in blue is the IUPAC name. IUPAC name is the naming that is following the International Union of Pure and Applied chemistry system. Okay, the proper way to name. But in bracket, the black colored one is common name. Okay, it's like unofficial name. Or if for a person, you have your official name that is in on your identity card IC, but also you may also have another nickname, right? Maybe your friend calls you slightly different. So the black color one is common name. For example, if there is only one carbon, it is normally known as formaldehyde. Okay, so formaldehyde is mainly used as a what you call a preservative for specimen. Okay, and then for biological specimen, and then you have acetaldehyde, 2 carbon, propionaldehyde, and also for butanol, also known as butyraldehyde. Okay, here is another example. If there is substituents attached to the carbon, so as well we same as previously, you have to check the longest chain containing the C double bond OH, and this carbon that is C double bond O will be carbon number 1. Okay, it will always be carbon number 1. So 1, 2, 3, 4, or you can also 1, 2, 3, 4. Okay, 1, 2, 3, 4, or it can also be 1, 2, 3, 4. So you see at the name over here, it is written as 2-methyl butanol. Is it correct or not? Anybody want to answer? Is it correct or is it wrong? Betul atau salah? The naming or the numbering.
Salah sir.
So if it's wrong, then what is the supposed to be? I've told you the numbering should start from here 1, 2, 3. Right. So the name should be 3-methyl butanol. Okay, not 2-methyl butanol, because this will also be counted as carbon number 1. 1, 2, 3, 4. Okay, or you can also 1, 2, 3, 4. Okay, instead of 1, 2, 3, 4. Okay, because the C double bond H will be, this carbon will be carbon number 1. Okay, so take note of this. And then in the presence of a double bond or an alcohol group, the aldehyde group takes priority, meaning you have to prioritize it. So example, another example over here, we have this is the same. Okay, this is the same 3-methyl butanol. Another example, you have a double bond. So the longest carbon chain is 4 carbon as well, 1, 2, 3, 4, but the numbering must always start from the C double bond O. So 1, 2, 3, and 4. Okay, 1, 2, 3, and 4. So from butane, it becomes butanol. But then again, there is a double bond over here. So you may write it as 3 to denote that the position of this double bond, 3-butanol. Okay, not butanol, butanol. Okay, because the root name for this, if there is no C double bond O, will be 3-butene. Okay, butene. So now it become 3-butanol. Okay, and then if there is a hydroxy group, so even if there is an OH group, C double bond O will take precedence. Okay, it will have higher priority. So the numbering will start from here, 1, 2, 3. Okay, if you have two OH group, so once this OH, when the hydroxy group become a substituent, okay, the name will be called as hydroxy. If it become the parent name, it will be known as, you have to replace the OL at the end. But the OH, when it become a secondary substituent, then it will be known as a hydroxy. So when there are two, it will become dihydroxy. So there are three carbon, okay? So propanal, and the position of the hydroxy is 2,3 dihydroxy propanal. Okay, 2,3 because the position of this OH at carbon number 2 and also carbon number 3. 2,3 dihydroxy propanal. And then for cyclic aldehyde, okay, if the carbon are in a cyclic form, so you have to add the suffix of carbaldehyde. Okay, so most of the other aromatic aldehydes have common name. So if you see a benzene ring become an aldehyde, they are mostly having some other common names. But for cyclic, for example, like this one, you have C double bond O H, and the R group is a cyclopentane. So why cyclopentane? There are 5 carbons, 1, 2, 3, 4, 5. So cyclopentane, but it is also has become sort of like a substituent. So the name now will be called as cyclopentane carbaldehyde. So this is to denote the carbaldehyde. Okay, and then for benzene ring, it is converted from its roots name benzene. It become benzaldehyde. Okay, you have C double bond OH. If there is another hydroxy group, okay, it will be known as salicylaldehyde. But for benzaldehyde, you can also name it as benzene carbaldehyde using the same method. Okay, and this one will be 2-hydroxy benzene carbaldehyde. Okay, 2-hydroxy because this OH is at position carbon number 2. Okay, this C double bond OH will always be at carbon number 1. Then we go for how ketones are named. So ketone, the suffix that you will be using is ONE. Okay, pronounced not as one but on. So the chain is numbered so that the carbonyl carbon has the lowest possible number. For example, here we have 3 carbon. So instead of propane, if it is an alkene, it will be known as propanon. Okay, propanon. And for this one, it is equidistant, meaning if you start numbering from here, it will still be the same. 1, 2, 3, 1, 2, 3. Okay, from the left or from the right, it will still be the same number. Another example, so there are 4 carbon, 1, 2, 3, 4. So from butane, it will become butanon. Okay, but the numbering, okay, let's say you start from this side, it will be 1, 2, 3. So the C double bond O will be at carbon number 3. But if you start from the left, 1, 2, 3, 4. So if you start from the left, the number will be at carbon number 2. So lower than if you start from the right. So it can be written as 2-butanon. And then another example, here you have 5 carbon, 1, 2, 3, 4, 5. Okay, 5 from pentane to pentanon, and the number 1, 2, 3, 4, 5. You get here number 3, but if you start from this side also, 1, 2, 3, 4, 5. Still the same, it will be number 3. Okay, so example 1 and example number 3 is what we call as symmetrical ketone. So the position of C double bond O is the same distance from the left or from the right side. Okay, but here the second example is what we call as unsymmetrical. Okay, unsymmetrical ketone. Okay, this one is propanon, where it is drawn in a open skeletal. Okay, so you draw all the hydrogen, and what is the name for this ketone? So let's see the number of carbon. You have 1, 2, 3, 4, 5, 6. So 6 from hexane to hexanon, and the position of C double bond O, if we start counting from here, 1, 2, 3, 4, 5, 6. But if you start counting from the left, 1, 2, 3. Okay, 1, 2, 3. So you start from here because 3 is lower than 4. So the name will be 3-hexanone. Or it can also be written as hexane-3-one. Okay, so this one is also correct, or you may also write as 3-hexanone. So other examples for ketone in a cyclic structure. Oh, sorry. Okay, if it is in a cyclic structure, here we have cyclohexane. Okay, so from cyclohexane, it will become cyclohexanone. And this one, from cyclopentane, there are two substituents. You have methyl group and you also have C double bond O. So always pick C double bond O as carbon number 1. So you already know that it will be, the name will become cyclopentanone. Okay, and then there is a methyl group over here. So 2-methyl cyclopentanone. And this one is a ketone, but it also contains a double bond. So when you have two substituents in the same compound, so carbonyl group will take higher priority. So start numbering from so that the carbonyl group will have the lowest possible number. So 1, 2, 3, 4 instead of 1, 2, 3. Okay, so we want to give number 2 to the carbonyl group. So 2, it will become, there are 4 carbon, so the name will be butanone, but then again there is a double bond over here. So this double bond is at carbon number 3, so that's why it is written as 3-butenone. But then you have to make sure that uh, people will know where is the position of carbon number 2. So it must be written this way, 3-butene. So this number 3 is for the double bond, butene, T-E-N, butene. And then -2-on, this number 2 tells you that the position of the ketone is at carbon number 2. Okay, so you have to write it this way. And then for aromatic, it have their own common names, like this one. If the structure is C double bond O and then you have R group CH3 on one side and a benzene ring on one side, it will be known as acetophenone. So aceto because you have this 2 carbon over here, aceto, and then this is the phenone. Or another name can be methyl phenyl ketone. So methyl is this, phenyl is this one, ketone. Okay, if there are 2 benzene ring attached together, so it may be known as diphenyl ketone, diphenyl group, or benzophenone. And this one, if you have a cyclopropane attached to the carbon, so it will be dicyclopropyl ketone. Okay, the name will be dicyclopropyl ketone. But what happens if the C double bond O is a secondary substituent? So on a molecule with higher priority functional group, okay, C double bond O and C double bond OH will be the secondary substituents. So it has its own name. So if C double bond O, the name will become oxo. And for aldehyde C double bond OH, it will be known as formyl. So aldehyde will always take priority higher than ketone if the same structure contain 2 hydroxy group, two carbonyl group, one is aldehyde, one is ketone. So always pick aldehyde has the highest priority. So example, we have this structure. So if you look at the number, first we count the number of carbon. 1, 2, 3, 4, 5. So there are 5 carbon. So the root name will be pentane. Okay, the longest chain, 5 carbon, pentane. And then we check how many C double bond O that it has. So 1 and 2. This one is an aldehyde because it is C double bond OH, while this one is a ketone, C double bond O, R and R. So aldehyde priority is higher than ketone, so you have to select this aldehyde as the parent name. So from pentane, it will become pentanal. And once it takes higher priority, the numbering will also start from this carbon. So it will be 1, 2, 3, 4, and 5. Okay, 1, 2, 3, 4, and 5. So the name will be, the root name is pentana. And you also have this substituents, methyl, okay, 3 methyl, and another one 4 oxo. So the name will be 3 methyl 4 oxo pentanal. Okay, 3 methyl 4 oxo pentanal. Why pentanal? 5 carbon, okay, with aldehyde having higher priority, so pentanal, and then 3 methyl CH3 at carbon number 3, and then 4 oxo C double bond O at position number 4. Okay, so if you have C double bond O, it will be named as oxo if it is a secondary aldehyde. Okay, sorry, if it is a secondary substituent. If there is no aldehyde over here, it's just a normal carbon, then this will be a ketone. But there is aldehyde and ketone, so the name will follow aldehyde, oxopentanal. This one, if it's an aromatic structure, you have benzene ring, you also have C double bond OOH, so this one is a carboxylic acid, which is a benzoic acid, and then you have C double bond OH, which is an aldehyde. So that's why the name become 3-formyl. So this one, 3-formyl benzoic acid. Why number 3? Because it is at position number 3 with respect to the C double bond OH. 1, 2, 3. Okay. So aldehyde higher priority than ketone, but carboxylic acid has higher priority than aldehyde and ketone. So what is the name of this aldehyde or ketone? So one way, first check the number of carbon. So this one has only one carbon. So if there is only one carbon, you already know that the root name, if it's an alkane, is methane. Okay, then check whether it is an aldehyde or an ketone. So if ketone, there must be 2 R group, but here both sides are hydrogen. So the name from methane will become into aldehyde. You will change into aldehyde. So the name should be methanol. Then we will go to the properties of aldehydes and ketone. So the carbonyl group is polar, okay, due to the greater electronegativity of oxygen. So oxygen value of electronegativity is 3.4, while carbon is 2.6. So polar, meaning that between the C double bond O, there is differences in electronegativity value. So this will influence the properties of aldehyde and ketone, such as the solubility. Okay, all of this is due to the carbonyl group being polar. Okay, you have C double bond O. So this carbon is slightly positive. This O is slightly negative because the value of electronegativity of carbon is, for oxygen is 3.4. So higher, meaning that it is slightly negative, while carbon 2.6, less than that, so slightly positive. So the electrons that is in the bond over here is being more attracted or pulled by the oxygen. So small aldehydes and ketone. So the word small here meaning low number of carbon. Okay, let's say you have the structure contain only 2 carbon, 3 carbons, 4 carbon. Okay, large aldehyde and ketone, meaning the number normally be more than 10, for example, or it can reach up to 20. So that is large size aldehyde and ketone. So for small aldehyde and ketones, they are water soluble, okay, due to the reason that it can form hydrogen bonding, okay, between the lone pair on the oxygen of the carbonyl group and the hydrogen of the water. So how do you know whether it contains lone pair or not? Okay, you can go back and refer to how you draw the Lewis structure. Okay, how you draw the Lewis structure. So on this oxygen, there are two lone pairs, 1 and 2. Okay, here, this is how the hydrogen bonding form. So you have the ketone, or it may also be aldehydes. So it form hydrogen bond with molecules of water. So as size increases, solubility decrease, okay, due to the interference in hydrogen bonding by the hydrocarbon tails of aldehyde and ketone. So what is the hydrocarbon tails of aldehyde and ketone? The R group. Okay, that's why if the small aldehyde will normally have low number of carbon, 1, 2, 3, 4 carbon. But as the R group becomes larger, meaning let's say if you have 15 carbon attached on this side, and also on another side can be another 8 carbon. So that R group is non-polar. Okay, so it will decrease the solubility of the whole structure of aldehyde and ketone. For example, you have acetone and also acetaldehyde are miscible in water. Acetone is ethanol. Okay, if you have 2 carbon, so mainly, and also acetaldehyde is ethanol. So acetone is what you call mainly used as uh, uh, the nail coloring cleaner. Okay, if you put color on your nails, so it can be used to clean all of those paint back. So acetone and acetaldehyde are miscible in water, but if the number of carbon on the R group become larger, it will make it less miscible. Okay, it become immiscible in fact. So on to the boiling points and intermolecular forces. So the general increase in boiling points from alkene to aldehydes or ketone and alcohol is due to the intermolecular forces between each type of molecules. So for alkenes, normally they are only held together by van der Waals forces. Okay, these forces increases with the size and length of molecule. So larger number of carbon, larger forces or van der Waals forces. And then the polar carbonyl group in aldehydes and ketone means that as well as van der Waals forces, these molecules are also held together by dipole-dipole interaction. Okay, because the availability of the polar carbonyl group, okay, so it has another type of force which is dipole-dipole interaction. While alcohol are held together by van der Waals forces as well and dipole-dipole interaction. So in addition, these molecules can also form hydrogen bonds with each other. So with each other meaning if you have ethanol, two ethanol molecule side by side, they can form hydrogen bond. But for aldehyde and ketones, even though they may contain C double bond O, which is polar, if there are two aldehyde of the same molecule, they cannot form hydrogen bond with each other. You can only form hydrogen bond with, let's say you add water, for example. So this one, so more polar, so higher boiling point than comparable alkane or ether. So it cannot form hydrogen bond with each other. So this hydrogen bond with each other, but it can form hydrogen bond with, let's say, water, ethanol, if you add. So lower boiling point than comparable alcohol. Example, butane. So this is alkane, boiling point 0 degrees Celsius. And this is ether, methoxyethane, slightly higher. And then you have aldehyde, propanol, increase to 49 degrees Celsius. And then it will become a ketone. The boiling point slightly increased by 6 degrees Celsius, 56. But once it become alcohol, the boiling point is almost the same as water, which is 97. Okay, due to the reason that the alcohol structure can form hydrogen bond among each other. Okay, so this side is also another type of example. So you have uh, uh, aldehyde over here, and this one is just alkene, okay, and alcohol. Both are having the same number of carbon. 1, 2, 3, 4. 1, 2, 3. Sorry, this one is only 3. This one 1, 2, 3 as well. Okay, so comparable alkene, aldehyde, and also alcohol, but very differs in terms of their boiling point. So on to the method of preparation. So how do we obtain aldehyde and ketone? Mainly, they are readily available in nature, meaning we can find them on plants, okay, and maybe on animals, and we can extract them. But some still need to be synthesized. Okay, so these are some of the example of naturally available aldehydes and ketone in which that it can be extracted. The first is example of benzaldehyde, which is oils of almonds. Okay, if we have almonds, which is in Malay we call it badam. So the essential oil obtained from the almonds contain benzaldehyde. And then from cinnamon, okay, if you do a lot of cooking, if you use cinnamon, the taste that give the cinnamon this specific flavor is what you call cinnamaldehyde. So this is the chemical component that actually contribute to the cinnamon taste. Okay, same as well for vanilla. So this is vanilla bean. Okay, if you go to the supermarket and buy vanilla extract, okay, or sometimes you have vanilla flavoring, that is actually just plain vanillin. Okay, unless if you purchase this vanilla pot itself, then it will be like uh, natural. But if you go and buy vanilla flavoring, so that is just vanillin, which is synthetically made. Okay, so this is aldehyde, aldehyde, aldehyde. Example of ketone, you have here carbon, which is the essential oil from spearmint, so a type of plant. And this one is camphor, which is this one, also obtained from plant as well. Okay, these three in which that you can obtain this white sort of like powder. Okay, in Malay I think it is called kapur barus. And then oil from jasmine. Okay, jasmine tree, bunga melur. The ketone name is called jasmone. Okay, jasmone. So these are some of the uh, naturally available aldehydes and ketone. Okay, but if you want to synthesize them or synthetically made, like for example vanillin, most of them nowadays are synthetically made. Okay, because this uh, vanilla pot or vanilla bean is quite expensive. So most people, if you want to make cakes, okay, mainly will buy the vanillin flavoring or vanilla flavoring. Sorry. So there are a number of ways, okay, in which you can synthesize aldehyde and ketone. So I have put here 4 types, okay, depending on the type of starting material that you want to use. Okay, if you have alkenes, so the reaction will proceed via ozonolysis. Okay, if you have alkyne, then you can just hydrate it. Okay, hydration via enol. If you have arenes, arene is aromatic compound like benzene. So you can obtain aldehyde ketone through Friedel-Crafts acylation. And then if you have alcohol, then it can be converted into aldehyde and ketone through oxidation reaction. So let's see the first example, which is ozonolysis of alkene. So alkene must contain C double bond C. Okay, so there must be two types of reagent in the reaction. One is ozone. Okay, ozone is O3, which is this one. O oxygen, okay, 3 oxygen. And you must also have a reducing agent. So on the first example, uh, this is dimethyl sulfide can be used, or another type of reducing agent that you can use is also zinc. Okay, can also use zinc as well. So the product that you will obtain is both aldehydes and ketone. Okay, you are going to get both because it is sort of like a cleavage happen in the middle. Okay, it's like this structure of C will be cut in half. Okay, so it will be cut in half. So you are going to end up with both aldehydes and ketone. Okay, aldehydes and ketone. The second way is through the hydration of alkyne. So methyl ketones can be prepared by the hydration of terminal alkynes, which is catalyzed by acid and mercury ion. So hydration of terminal alkyne will use uh, mercury sulfate, HgSO4, sulfuric acid, and water for methyl ketone. But uh, for aldehyde, it will use silicon borohydride, okay, followed by hydrogen peroxide in sodium hydroxide. Okay, so depends on the product that you want, methyl ketone or aldehyde, you have to use different reagents. Okay, but uh, here an example, we have one octine. So why the word octine? Because there are 8 carbon. Okay, one here, 2, and then 3 with another 5 here in the middle. So 8, and then 1 to denote the position of the alkyne, C triple bond C. Okay, C triple bond C. Then you have H plus, which is from the acid. Okay, acidic medium, water, and also the mercury ion, which is from the mercury sulfate, Hg2 plus. So you are going to end up with this ketone, okay, 2-octanol as the product. And then the third synthesis method is Friedel-Crafts acylation of arene. So the starting material can be benzene or any benzene with substituents, for example. And the reaction must proceed by the use of either acid chloride or aluminium chloride, okay, to get ketone. And also there is another type of reagent that you can use, which is carbon monoxide, sulfuric acid, with the presence of aluminium chloride or copper chloride, and benzene. Okay, benzene will always be the starting material. Okay, here an example, you have benzene, this benzoyl chloride, which is acid chloride, in the presence of aluminium chloride. So the function of this aluminium chloride, which is a Lewis acid, is basically to act as a catalyst. So what will happen is the chloride over here will be removed, and the bond form is at this C double bond O, it will straight away form a bond with this carbon. Okay, you're gonna get benzophenone. Another structure over here, to obtain benzaldehyde. So this is the product that you will get will only be benzaldehyde. Okay, and the reagent used will be carbon monoxide, hydrochloric acid, and aluminium chloride or copper chloride. Okay, so here another example, you have benzene plus this acid chloride, CH3 C double bond OCl. So in the presence of aluminium chloride as catalyst, So what kind of product that you will get? So as I said earlier, the chlorine will be removed on this side. So this C double bond O will form another bond directly to any of this carbon. Okay, you have 6 carbon selection. Let's say on this one. So it will form the product once the bond is formed. And the last type of synthesis method is the oxidation of alcohol. Okay, but this time around, you have to check what kind of product that you want, whether it's ketone or aldehyde, because different types of alcohol needs to be used. A secondary alcohol will give you ketone, while a primary alcohol will give you an aldehyde. So this reaction will need oxidation agent. Okay, here we can use sodium chromate. Okay, or you can also use pyridinium chlorochromate. Okay, aldehyde and ketone are mostly prepared by the oxygen of primary and secondary alcohol respectively. So chromium reagent such as PCC are commonly used in the laboratory. So another type is sodium chromate may also be used, or you can also use potassium chromate. This one, the difference is just Na plus and this is K plus, okay, potassium. So this is an example, okay, a question. So you can add this, try to answer this in your tutorial as well. So I have put tutorial, so maybe you can add this question later. So let's see the reactivity for the carbonyl group. So before we go to the reaction part, we'll look on the reactivity of the carbonyl group. So what kind of reaction does a carbonyl compound can undergo? So although double bonds require more energy to break than single bond, compounds with double bond tend to be more reactive as addition reaction are possible. Okay, so you have C double bond O, they prefer to have addition reaction, meaning you add something to the reaction. So some of the chemical properties of aldehydes and ketones result from the polar nature of the C double bond O bond. So the positive charge on the carbon atom makes it open to attack by nucleophile. So what is nucleophile? Nucleophile is any species, okay, or any reagent that are electron rich, meaning they have a lot of electron and they want to donate, they want to give that electron away. So aldehydes and ketone can be reduced, forming primary and secondary alcohol respectively. So here is the C-O, okay, polarization of the carbonyl group. So aldehydes may also be oxidized to carboxylic acid. So if you reduce aldehyde and ketone, you will get alcohol, because earlier one way to synthesize aldehyde and ketone is through the oxidation of alcohol as well. Okay, if you further oxidize aldehydes, they may be turned or converted to become carboxylic acid. Sorry, let me remove this. Excuse me, yeah. Okay, this one. Okay, sorry. So let's see the first reaction for aldehyde and ketone. Number one will be the reduction. Okay, reduction reaction. So what will happen in the reduction reaction is basically a gain of hydrogen, H2, and also a loss of oxygen. Meaning that you want to add two hydrogen, okay, two hydrogen, which is this one, two hydrogen, to this carbon, and a loss of oxygen. So a reduction of a carbonyl compound in general will give you alcohol. Okay, note that organic reduction reaction add the equivalent H2 to a molecule. So this will be your carbonyl compound, and then you have this reducing agent. Okay, this H in bracket is a generalized reducing agent. Then you are going to end up with alcohol. So aldehyde will give you primary alcohol, while ketones will give you secondary alcohol. Why? Because aldehyde over here, C double bond OH will give you primary, because it is gonna add one hydrogen to this side. So the carbon will only be bonded to one other carbon to this side. So the carbon will only be bonded to one other carbon, which is this R group primary. Ketone will give you secondary. So the reducing agent normally used or commonly used, the first one is lithium aluminium hydride. Another types of reducing agent can be sodium borohydride. Okay, so these are the two most common reducing agent currently being used. Okay, then all of the next reaction, okay, after this are basically an example of nucleophilic addition reaction. So this is basically a type of reaction very specific to aldehydes and ketone. So the word here nucleophilic, meaning the reaction involve a nucleophile, a very electron-rich species. Okay, the symbol is written as Nu with double dot over here, which is electron, and a dash. So this is negative charge. Okay, and it also proceeds via addition, meaning you are adding. Okay, so this is a general way how nucleophile is being added to a carbonyl group. So here the nucleophile will come in and attach to this carbon. Okay, attach to this carbon. This electron will move to this oxygen. So this oxygen will become negative. And then the removal of water. Okay, addition of water with the addition of water. So this oxygen will take one of the hydrogen. So this is the product. So nucleophiles attack on the carbon atom of a carbon-oxygen double bond because that carbon has a partial positive charge. So the pi electrons of the C double bond O bond move to the oxygen atom. So this is just the general reaction for the rest of the example, which is the first example is the addition of water. So if you want to add water, so in acid, the water will act as a nucleophile, but in base, hydroxide ion will be the nucleophile. So aldehydes are more electrophilic since they have fewer electron donating alkyl groups. So example, you have aldehyde over here. So if you add water, the product that you are going to add will be a diol. So it is an alcohol, but it contains two hydroxy group. So it will be known as diol. Same here, if it's a ketone, if you add water, the product will also be a diol. The only difference is the R group. Okay, you have to check the R group must be the same, but the addition will still be 2OH group diol. And then you have this formation of imine. So another type or another example of nucleophilic addition reaction in which you form the imine. So here nucleophilic addition of ammonia. So ammonia is NH3 or primary amine. Which is primary amine? This is the primary amine, RNH2, or ammonia. Ammonia can be NH3. So the product that you are going to get is you are having this C double bond N. So this is what an imines looks like. If you have C double bond N, so this is an imine. Okay, so the ammonia or primary amine will come in and attach to this carbon. Attach to this carbon, and the oxygen will be eventually removed. Okay, it will be eventually removed. You see that the rest are still the same. CH3 is still there. This pH is actually phenyl, which is a benzene ring. Still there, the same. The only difference is from C double bond O, it becomes C double bond N. Okay, R is basically whatever that is attached to the amine. And then you have the addition of hydrogen cyanide. Okay, the product that you are going to get is what you call as cyanohydrine. Cyano because you have the C triple bond N. Hydrine comes from the OH. Okay, so but nowadays the hydrogen cyanide of HCN are normally being replaced. Okay, they are replaced with sodium cyanide NaCN or potassium cyanide KCN in base. Okay, then they protonate to a hydrogen. Okay, because this hydrogen cyanide are highly toxic. So reactivity for the reaction, you have formaldehyde. Formaldehyde is basically C double bond O H2. C double bond H2, and then normal aldehyde, ketones and bulky ketones. So this is the same. Okay, nucleophile addition reaction of cyanide. So the dangers of HCN. So hydrogen cyanide is highly volatile liquid which has faint bitter element. So in solution, this hydrogen cyanide partially dissociate to become hydrogen ion and also cyanide ion. So it is highly toxic because it inhibits mitochondrial enzyme that is essential for respiration. So basically, it will affect our breathing. Okay, being so volatile and flammable. So when it become volatile, it means it is easily turned into gas. So when it become gas, human can easily inhale. Okay, we can smell, inhale it, and it will affect our breathing. Oh, sorry. Wait, yeah. I think I'll use. Sorry for that. Okay, and to the last type of reaction, which is Wittig reaction. So the name is known as Wittig reaction. So this is basically a nucleophilic addition of phosphorus yelide. So what is a phosphorus yelide? This is the structure of phosphorus yelide. It's slightly complex, but the product you are going to get is alkene. Okay, so alkene can be converted to become ketone or aldehyde. Okay, through the ozonolysis, and aldehyde and ketone can also be converted back into alkene, okay, by the use of this phosphorus yelide. Okay, this is just general reaction pathway. And the last thing or the last slide will be how aldehyde and ketones can be distinguished, okay, through chemical reaction. Okay, how are you going to differentiate if you are given uh, two beakers? Okay, determine which one is aldehyde and which one is ketone. One reaction you can do is the Fehling test, and another one is Tollens reagent test. Okay, if you do the Fehling test, which is adding Fehling solution to aldehyde or ketone, so aldehyde will give you reddish orangish color, okay, solution, while ketone, the color of the solution will remain blue, meaning unreacted, okay, for Fehling. But if you add tolerance reagent, if you do tolerance reagent test, aldehyde will produce this silver mirror on the wall of the glassware, or it may also form black precipitate. But for ketone, there will be no reaction, meaning the solution will remain unreacted. So clear solution. Okay, clear solution all the way. So this is how aldehydes and ketone can be differentiate, okay, in terms of using a chemical test. Okay, so basically that is